Phil, thanks a lot for the invite and for the kind introduction. Yes, so as the images in front of you show, most of the work that you'll be seeing is people interacting with objects, mostly using their hands. However, over the course of my career, I'm generally interested in video understanding and action and activity. But I'll kind of focus in this talk on the fine-grained understanding with which in computer vision we're still lacking on this. So I'm hoping that by the end of the talk, you'll see what's lacking and where small contributions have been made by myself and the team. So we'll start with an example. And this is an example from a wearable camera of someone performing a task in their kitchen. So this is something we can very well understand. Probably we've all done a similar task using maybe a different tool. But what's different between the majority of video understanding methods is that they typically target what we call coarse-grained understanding. So taking videos online and separating videos of someone cooking from dancing from swimming. This holistic understanding of video is very popular and very interesting. However, there is an interest also in doing something more fine-grained, like identifying not only the step in which the person aims to add garlic to their meal, or maybe a finer grained understanding of the exact step where they're smashing the garlic as part of adding the garlic. And being able to achieve a level of perception that can allow us to answer questions like, when exactly was the garlic smashed? Or how was the garlic smashed? Or why is this person smashing garlic? Hopefully not because they hate it so much they want it to break. Or how skilled is the person in smashing the garlic? Or are we done now? Or is more effort needed to smash the garlic further? And then what information do people who look at such a video use in making such decisions? Because we all can answer most of these questions. So of course, we all can model a change in appearance, but there are other things that are difficult to capture and necessary to answer these questions, like the motion, the force. It's pretty clear to us perceiving the video is that there is some force exhibited to achieve this task. Audio is so significant, and increasingly without it, if I show you the exact same video without audio, you might not be able to accurately answer some of these questions. And of course, the question is, can we just understand this from an RGB and audio and a video, or do we need depth? Do we need 3D? Is there more information required to achieve this level of perception, which is human-like? So first, to even attempt to ask these questions, you need a good collection of videos of natural object interactions. And that's the mission we started in 2017, to collect a large-scale data set of people naturally interacting with objects in their daily environment. And so we collected and released the data set and then extended it. And the final release last year was 100 hours of videos of people actually just doing stuff in their kitchens. The emphasis on kitchens is because in our daily life, this is the most complex human object interactions, similar to people maybe working in factories, but on the basis of a human just doing stuff in their daily life. Most of our object interactions are in the kitchen. So Epic Kitchens, which is this set of benchmarks and videos, started with an actual data collection, because these videos are not available online. People online might be recording very nice social media style footage of how they do stuff, but this is very different from how we interact in our busy and cluttered kitchens and how we interleave lots of tasks. So you might be picking something up and then washing the dishes and then coming back. So this level of understanding requires a data collection. We gave people cameras to take them to their homes and ask them then to wear these head-mounted cameras and then to collect everything they're doing in their kitchen for 3 full days, only in the kitchen. So they start recording when they step into the kitchen and they stop as they step out. The reason this has not been attempted like this before is the fact that it's very difficult to collect ground truth or labels for this type of task. So this is like hours and hours of data with no labels. To leverage something that is usable, we then went into what we call a live narration phase. So the same individual would then, after finishing the collection, just watch the videos and talk over them as if they're giving us subtitles to the brilliant movie of them cooking. And these live narrations in their native language form the base of collecting our dense action segment annotations. And the scalability, the fact that we, via this, made the method not only efficient and scalable, but possible to even scale to 100 hours of data collection and lots of people. And then in 2018, we released the first version, which was 50 hours on the style. And of course, you never do things perfect in the first round. So we went and did an extension for the data collection. We improved the way people do the narrations. And that kind of increased the number of actions per minute from 13 to 20. So it's fairly dense now and complete. And then we released last year the extended version, which is called Epic Kitchens 100. Currently, the dataset is very natural and thus very long-tailed. So on the y-axis, you see the log scale of the actions and the objects, and we're grouping them into one level higher of a hierarchy. So you can see appliances and vegetables and furniture. And in terms of actions, you can see people cutting and peeling and breaking as part of a splitting action, etc. And all this is available to community to utilize in any way they see fit. Currently, we have 5 very simple and open challenges in the dataset that do a very basic step in understanding its potential. For example, the standard action recognition challenge takes a pre-given start and end time and then expects the participants to then their methods to be able to predict the action and the object. So this is very, very refined. That means all the free-form narrations are processed into classes, etc. And we assume we have start and end times. So this is very far from solving the big problem of understanding the full extent of untrimmed videos. But over the past 2 years, people have been submitting to the leaderboard of this challenge. And we currently have the 3rd version of this challenge with another round of submissions to close on 28th of May. So if you're interested in Epic Kitchens, have a look. I'm more kind of keen to tell you how after we collected this data set, we were able to ask interesting fine-grained questions. And I'm dividing these into 4 categories of questions we've been asking as part of the group. One is how well is this person doing a particular action? There is a collection of works that focus on supervision and duality, vision and language, and audiovisual. And these are all fairly recent works that I'll just touch on in terms of topics, and I hope it won't be too overwhelming. I'll probably stop halfway through in case there are questions. So how well can we really look at a video of someone doing a task and understand from the video how well you are doing that task? Can we take, in this case, different people rolling a pizza dough onto a tray and assess them within that task according to their skill? And in this work, this started alongside Epic Kitchens, so it uses different types of data. But we start with the notion is we want to assess the relative skill. We don't want to give Olympic level scores to say 9.7. We just want to know if someone is doing something better than someone else. So we start with annotations, with people looking at pairs of videos and being able to assess, okay, not sure why they're not working, okay. Being able to assess if someone is actually exhibiting a higher level of skill, say in drawing. And then we collect evidence from people watching these videos and say, yeah, the person on the right definitely is doing a better job. And these form the labels both for training and for evaluating our method. So what does the method look like? And perhaps this will be a little bit of technical, but I'm hoping not too difficult for people to understand how computer vision now relies heavily on the notion of annotations and machine learning. So as input, we would get 2 videos that have been labeled as one exhibiting higher skill than the other. And then we would be looking at the whole video, extracting some level of features. And then we would be learning some sort of a scoring function that ensures that the first video is exhibiting a higher level of skill than the other. And as you feed more and more of these pairs of videos, you probably learn a sensible ranking function. However, different from standard ranking, in the case of people performing tasks and we want to exhibit their skill, not every part of the video is equally relevant to their skill level. Assuming they're, in this case, braiding hair, the bit where they're maybe combing the hair, that might not even be evidence of their skill. So you would want to weight these video parts by their relevance, and we call this an attention module. So you can learn a weighting for the various parts of the task. And in this work, we showed that you can't just weight it. You really need to make sure that you outperform uniform. Otherwise, the performance doesn't really work. It kind of goes into a local minima. Even when doing that, we got good results, but we looked at the attention module and we realized that the method is not picking on mistakes. So mistakes were not getting very high weighting in what you think has to be the highest weight in your skill level has to be if you do mistakes. And the reason is that the ranking function relies on what we call shared weight. So it expects that thing to appear both in the good videos and in the bad videos. And if it doesn't, it cannot give it a very high weighting. So in this work, which we presented in CVPR now a couple of years ago, we introduced multiple attention modules. And until this point, they're exactly the same. But we make them specialize by a loss function that makes one of them attend to what's good in the video and one attends to what's not so good. And all of this is done in a learning manner. So if we look at what this brings out, so this is what ends up as being an evidence of low skill. And you would see, for example, in the case of people putting an eyeliner, they're removing bits of what they've done. And that has been consistently picked up as evidence of low skill. Or in origami, people undoing what they had done. And in the case of high skill, you see people firming up, or you see people kind of finalizing. It's interesting that the same behavior is learned as high skill in certain tasks and low in another. For example, in the last example, this is a person stopping to think, basically hesitating. And this is evidence of high skill in drawing, because if you just go and draw something, you don't know what you're doing. But evidence of low skill, for example, if you're putting makeup. If you stop and think, you probably... So that's the magic of learning now in computer vision, is that these things we couldn't have even thought of as handcrafted decisions. If you're interested in any of the works, please look at the relevant papers. We have code and etc. But I wanted to give you an overview of the flavors of the problems we're trying to solve. Similar to the level of skill, there is the question of whether you actually succeed in performing a task. And we call this action completion. Probably not the best name, but that's what we called it. So this is looking at someone doing a task, say, for example, blowing candles, and being able to detect the moment to which all your candles have been blown out. So you'll see the ground truth compared to the model we're proposing, where orange is before you complete, and then purple is after you complete. So trying to predict the moment of completion, as well as predict when you actually finish the video and you don't succeed. So you kind of, this poor kid keeps blowing these candles that never go away. And we've tried it on a number of examples, people drinking or picking up from the floor. I thought these things are really hard, but there is a subtle motion that people kind of move up and like they pick something up. And it's very different if you fail to pick something up. So there is a lot that you learn from the examples on action completion. And these two works are really on understanding how well has someone done something, and quite different to lots of approaches that have looked at video understanding. So that's the first bit. The second bit is, what can we learn from? And this is a work on different levels of supervision. This was presented last CVPR, where we're looking at a video of someone doing a task, say, for example, mixing something in the pan, and these are examples from Epic Kitchens. And the standard way currently in doing that is to look at both the RGB and the optical flow, the motion, and then you average the prediction. If we learn good examples of people perform a variety of tasks from one kitchen, then we try to recognize the same set of actions, but in another kitchen, we know that this is a particular problematic thing in computer vision. And if we look at the feature space, which is what the model is learning, we'll realize that there is complete split between what we call the source, so the space from which you learn, and the target, which is this other domain that you're trying to predict in. They don't even overlap. So there is no point in taking the decisions that learned in one environment to map it to the other. But the question is, can we improve this without having to do more labeling? So what these methods do is that they actually try a number of tricks. And in this proposal, we tried something called the self-supervised loss function. And that loss function, what it does is that it simply tries to say, are these two modalities coming from the same action or from a different action? Because we have extracted RGB and flow from the same point in time. So it's very easy to give corresponding and non-corresponding modalities. And then you just say, is it corresponding or is it not corresponding? You don't need labels for that. That's why we call it self-supervised. And just by doing that, you'll see that the target, which is examples from this other kitchen, are getting really nice clusters, because you're really finding this correspondence between the image and the motion. But they don't really very well overlap. But we have a good trick in overlapping them, which is doing something adversarial, not being able to distinguish between whether the data is coming from kitchen 1 or kitchen 2, source 1 or target. So in that case, you try to predict the domain or the kitchen, and then you try to reverse that decision using a gradient reversal layer to remove any features that make that distinction. And we have 2 of these on each modality. So we have an adversarial part, a self-supervised part, and then a classification. The source is labeled, the target is completely unlabeled. And by doing that, we were able to kind of relate some very interesting actions. So you have now an example of someone cutting in source and in target. And if you only look at the source only domain, they're very far. If you add only the self-supervision, which is the main novelty of this work, they are closer, but they don't fully align. And in this combined approach, they really align, and we can recognize these cutting actions in a new environment. Another work that I really like, it was presented in a workshop, but I think is really interesting to look at, is this notion of what's a video? So I'll show you a video, and the question is to try to do action recognition. What's the action that is taking place in this video? And hopefully a few of you believe that this is a person closing a Tupperware or a box. This video, in fact, was never captured. This is the video that was captured. And what you've seen now is a time reversed version of this video. And I'll show it again so you don't feel very tricked. So this is the person, this is the time reversed video. This is the actual video. And the question we wanted to ask, whether the video on the left, which is time reversed, could be used to learn closing boxes. So it's a time reversed video of opening boxes, but is it a good training example for closing? It's completely artificial in the sense that it's time reversed, but it comes from real frames. So we said, okay, you can time reverse a video and produce examples of the same class. And these are valid examples. And we showed using a perceptual study that people fully believe these are valid examples. You can also reverse a video and produce an example of a completely different class. And actually, if you reverse examples of that class, you come back to class A. So these are, we call them equivariant classes. And of course, there are cases where you reverse videos, they break the law of physics, things pop from the floor. Interestingly, the black section, this has been very well studied in computer vision under the notion of the arrow of time. If you reverse time, things break. But in object interactions, the first 2 examples not only exist, but are very useful. So in this work, we have trained in what we call a 0-shot setting. That means every example here, you have a class for which you have examples. You time reverse those, and you train for that other corresponding class. You test with real examples of both classes. So the test set hasn't changed. It's just the training now for every other class in this set is 0-shot. You've never seen the real examples of that class. And it even works for classes like digging something out from the floor, from the ground versus burying something. So you time reverse burying into digging, and then you test on digging, and you can really successfully recognize that class. Okay. And the final bit that I want to talk about under this duality is a work that will be presented this CVPR. I was hoping to integrate it into the slides. I successfully managed yesterday. And it's the idea of how many examples do we need to do what we call few-shot learning. Can we only, from 2 examples of someone cutting, learn a good classifier for cutting? In computer vision, this is currently done in the following setup. You have a number of very few examples in what is called the support set on a small number of classes. And what you're trying to ask is, given a query video, to which of these few shot examples in a small number of classes does the query belong? So you try to learn a classifier using this small scale support set. All prior works on few shot action recognition try to match the query to every video in the support set alone, sometimes actually time aligning the video to every video in the support set. Inspired by very novel approaches in images, it's called the cross transformer, what they do is that they take a patch in the query and they match it to all patches in the support set jointly. So they're not looking at pairs, they're looking at all the support set together. And in doing that, they produce what they call query-centered prototypes, but there is no position information. In the case of videos, you really need temporal information. So you can't really just take frames and match them to frames. Doesn't work in videos, because how can you distinguish someone, sitting down from standing up? You need time in videos. But inspired by this start, and a well-known approach in video understanding that represents a video by a random set of tuples, so 2 frames or 3 frames or 4 frames, we took this as the representation of the video. So this comes from a method called TRN, and we did few-shot action recognition as follows. We have the query video and the support set. We take combinations of pairs of frames in the query video and in the support sets. So these are paired. And then we do the standard transformer or cross transformer, where you try to find the match between your pair of video of frames in the query and pairs in the support set, all of them jointly with a softmax. So you're really looking at all of them. So if you're familiar with the transformer, this is a standard transformer. And what you come out at the end is a query-specific class prototype. And then you can use that to say to which of the potential classes does this query belong. And you can do that for pairs. You can also do that for triplets. You can do that for 4 frames. But single frames is really not so good because it's not a representation of an action. By doing that, we first started by looking at all possible pairs. And in the paper, we showed how you can not do exhaustive pairings, but I'll skip that bit. The good thing, of course, I like the idea more than the numbers, but it's good to say you outperform on all the different possible few-shot baselines, which didn't have very good clear benchmarks. So the code is already out there, as well as all these splits in one place, if you want to do few-shot action recognition. And it's important to say, where does the contribution come from? Particularly on data sets that have very temporal information, like this data set called something something v2, you see that single frames is a lot worse than taking these pairs or triplets of frames and combining multiple temporal cross transformers. So something with a pair and something with a triplet, similar to the figure you've seen, achieves the best possible result. And if we, and also it really, the performance of TRX, which is this temporal cross transformer, improves as you have more examples in the support set, because its strength is in finding the correlation across all the videos in the support set. So it's not much better on one shot, but clearly start outperforming the previous state of the art as we do 2 shots, so 2 videos per class, 3 videos per class, etc. And some of the qualitative examples, difficult really to see, but you can see that there are pairs of frames here in the query, and this is their best match in the support set. There is another pair of frames in the query, and it's matching a different pair in the support set, etc. And similarly for triplets. And it's interesting looking at some of these examples that you're actually matching, these 3 cases where it is falling and then appearing on the ground to a correspondence of falling and appearing on the ground, etc. Okay. I hope I have not already overwhelmed you. Before I go into the third quarter, if there are any urgent questions, you're going to forget the first two topics as I move forward. Do you want to take questions or keep going?
I guess if anyone's got a question, unmute and jump in.
I hope I'm not speaking too fast. I have that tendency.
It's all very clear so far. So yeah.
You're a biased listener, Will, but I'm glad. So, okay, let's move into, maybe as Will said, some of you might be more interested in the audio and in the language. So I'll tell you what we've been doing with vision and language, and then audio and language, starting with looking at actions and the relevance of the part of speech in text. So in this case, we're looking at the sentence. So this is the sentence. If you remember, I told you that these people who recorded the data for us, they spoke over it and gave us these live narrations. So this is the live narration as it was stated by the individual. And the question is, can we start from this text modality and then retrieve the relevant video, or the other way around? This is currently called cross-modal video retrieval, where modality here refers to text versus video. So in this work, we started with the standard approaches until we realized that most of these approaches tend to ignore the verb. The verb is really irrelevant. They just focus on the presence of meat and ball of dough. And that's because in computer vision, we're really good at recognizing objects, and we're still not so good in doing actions. We're still behind the object recognition community. So to really emphasize the importance of verbs, we then learned what we call an embedding space. So this is a space where we put the video close to the corresponding representation of the verb, and then a completely different space for encoding the video along with the nouns. So this is, we call this a verb embedding and a noun embedding. The main objective of the first one is really to understand what putting and what opening is, regardless of the object. And that was our objective. We spoke at some point to lots of people in NLP, and I said, I want to learn a representation of open, and I don't care about the object. And they were very unhappy with me saying there is no context and no sentence. So they didn't like that at all. So we made our attempt in trying to recognize a representation of only the verbs in the sentence. Of course, to do the full retrieval of text to video, you still need to incorporate these two modalities into one representation that then takes the visual representation and the text representation and can give you sentences. So this is how we go, but we go via these part of speech embeddings. That means that the same video is going via two projection functions. One only focuses on nouns and one only focuses on verbs. And the outcome is exactly what we were hoping to do. So this is a neuron in the embedding space of nouns, and that's one of them. And that is looking at, in this case, chopping board in all its actions. So it's being moved. People are cutting, people are washing on it, putting it, taking it, right? And in the same case, if you look at the verbs, this is a neuron that's learning how to open and close regardless of the object. So we're really kind of going back, maybe I'll go back into this video. So there is this noun space that groups all these examples that belong to a certain object, regardless of the action. This is the noun embedding space. And then there is the verb space that in the same place is learning open/close, regardless of the object. Now, we've shown in the paper that this allows you to do also novel combinations. So you can kind of now open an object you haven't opened before, because you have really learned what the object is and what the noun is separately. We've taken the part of speech one step further with a working collaboration with people in INRIA to learn adverbs. So can we learn things like slowly, quickly, partially, finely? And when we started with the idea, we were really not sure if this is something that we can learn purely from video, because slowly is really different depending on the verb. So if you're stirring slowly, that is very different visually than when you're moving something slowly. So the visual signature is different. And the question is, can you still, but we really know what it is. There is a concept of these adverbs, and it's very related to how people do actions. Prior work has successfully learned adjectives like sporty, new, old, red, green. But this was the first attempt to look at adverbs. And I'm really grateful to Hazel, the student who worked on this, that she took a really difficult project and tried to push it to its end and to a good publication. So we start in this case from YouTube videos because our dataset doesn't have that rich representation. These are instructional videos where people mention specific adverbs where people need to do something in a certain way. So roll your lemons quickly. And then what we wanted to do is, again, this is an embedding space. So you want a video and a text to be close to one another. What we want is to make the video not only close to its corresponding action, but to a modified version of that corresponding action, such that it is not only rolling, but it is rolling quickly. And this modifier we wanted to share across all verbs. So we wanted to generalize the concept of quickly to all possible verbs. And it would have been nice and easy if we had really good labels, but we don't really have a very well localized action and adverb. And so we had to incorporate a bit of an attention over. So the sentence comes from the YouTube subtitle. We have a video near it, but not exactly perfect. So again, we introduced a level of attention where the query in that attention comes from the verb. So we know we're looking at a rolling action. We're using it to query where in the video the action really is. And then the output of it is then embedded close to this modified verb. So the main of the focus is to learn the modifier and the attention mechanism. And the output is really cool. So what you'll see is the boundary of the video corresponds to when the action mix is taking place. And then when the boundary is thick enough, the action is happening. And then we're predicting the corresponding adverb, in this case, quickly. And then we have cases where someone is kind of turning quickly. So again, we're looking to first localize the turn. And once that is done, then we predict out of a quite limited set of adverbs. But a good attempt to really understand adverbs in videos. And the last work to be presented this CVPR is a criticism of the concept of video retrieval. So video retrieval works, look at a video, a set of sentences, and you're supposed to rank or retrieve which of these sentences correctly corresponds to this video. This is action retrieval. Looking at a number of data sets in this, we realize there is a different problem. There are videos for which many sentences in those data sets are equally good to a human observer. Like, which of one would you actually pick? But the benchmark claims that one of these is good because this is the one collected with this video, and the rest are incorrect. They can't be retrieved. So we wanted to assess this problem, which we call instance video retrieval, that there exists one corresponding caption for every given video in the dataset and vice versa. And looking at a number of benchmarks, really popular benchmarks for retrieval, like UCOOK2, MSRBTT, we realize this is really, as in some sentences are a lot better than the potential ground truth, in our opinion, right? They're definitely closer than a band is performing for the crowd because there is no crowd in this video, but the ground truth is this first bold one. And similarly in Epic, because we also have one domain, we have a lot of narrations of the same corresponding action. What's the impact of this and how can we do anything better? Of course, the notion in these large data sets to then relabel what we call the relevance or the correspondence between the video of every sentence is impossible. These are thousands of videos. But what we did is we did a proxy. So we assumed that the caption is a decent representation of the video. And instead of labeling the whole data set as the correspondence between the video and the caption, we found a proxy function that relates the captions. And we proposed 4 different proxy functions depending on whether you rely only on words or on a part of speech, or on synsets, or even on the structure of the word, of the sentence. And from that, we were able then to look at the video and the set of captions. This is the ground truth according to the benchmark. We were able to find all the corresponding very valid ones, and then to look at whether methods recognize either the highest ranked one or the lowest ranked one. That all is okay. It should be okay. And to look then at the error bars of the current methods on these benchmarks. And that's where we realize, these benchmarks are really making ad hoc decisions, because these very large error bars are really huge. You really are unable to rank methods purely using this instance retrieval, and that applies to the number of benchmarks. We then went and said, okay, instead of using these binary correspondence, let's use our proxies. So this is the proxy based on the captions, and this is then some sort of a different sort of ranking where things are somehow relevant or not relevant. And we used NDCG instead as a metric. And we showed in the work that then all these methods that they say they outperform other approaches or basic approaches like a standard MLP no longer outperform. So they're not really doing anything better than a standard one. They're just doing some bias towards the way the data sets were annotated. And this is work that we represented this June. And finally, and I think I'm somehow on time, not really, I'm gonna skip the first bit on audio and tell you about the more recent bit of work, which is audio slow fast. I think it's really interesting. Sounds of interactions are of two types based on our observation. There are harmonic sounds, and that means there is a frequency. From the frequency, you really can figure out that there is water, but there are also percussive sounds. And this is in our dataset, Epic Kitchen, but also in other datasets. So this is a dataset called VGA sound, and similarly, action sounds are either harmonic or percussive. To capture both, in this work, to be presented in ICASP, and it's my first attempt to publish in ICASP, so thanks to our collaborators in Oxford, we looked at a two-stream architecture inspired by the slow-fast architecture in video, where we take as input two different representations. One is focusing on frequency with low temporal precision and large amount of channels. One is focusing on temporal resolution with fewer channels, and they have lateral connections and also separable convolution. So you convolve over time and frequency separately. And the results are really good. So we are able to really recognize the harmonic sounds and the percussive sounds and show that slow is really good at picking harmonics and fast is really good at picking percussive. Before concluding, there is a bit of work on what really models can learn. And in this work, we're taking a video. We're looking at what the model really learns in terms of how can the model make a decision on a certain class. So Will, who's led on this work, he really relied on the concept of game theory and really figuring out the contribution of every frame to the class decision. So there is the prior probability of a class, but actually each frame in the video has a different contribution to the class decision. And that can only be done by looking really at one frame, two frames, three frames, and looking at the difference between these. And that difference is the contribution of that frame, but you need to do that over all possible combinations of frame combinations. And he's done this by really finding an efficient way to do this. And so you can have also show that some frames really have a negative impact on the class decision. If they were removed, you will have a higher probability of predicting the class correctly. And he showcased then that, for a particular class, say in this case, twisting something, which frames exactly contribute to that decision and which frames have a negative contribution. And really, so this is an example of a class saying, show something is empty. And clearly, there are bits of the frames that are not related to showing something is empty, and the model is capable, the explainable model is capable of saying, these are really negative contributions to that class. And there is a dashboard that can allow you to play with lots of classes and see the impact of individual frame contributions. Last but not least, along with a large collaboration with a number of universities, we are releasing a large new Ego dataset called Ego 4D. This is the Bristol contribution to this dataset, but the dataset is really 11 universities. So if you're into egocentric, there is something even bigger coming outside kitchens. Not labeled in exactly the same detailed way as Epic Kitchens, but very, very interesting, particularly for self-supervision. And of course, I get the pleasure to come and present this to all of you, and wouldn't be possible without a very, very dedicated team, all of them working in hand-object interactions and contributing to the benchmark of Epic Kitchens. I'm guessing I'm not so behind on time, despite the number of slides I've presented to you.
No, perfect. And since it's always weird in these virtual talks not having any applause, thank you for a very interesting talk. So I guess if people have got questions, please unmute or put them in the chat if you don't want to appear in the video.
I thought I can remind you of the topics just in case you already forgot.
Good idea. I can maybe kick off with a couple. So actually, the new data set you mentioned at the end kind of relates to one question I was going to ask. There's a very high level question. So it seems like maybe, I mean, this is about like kind of scale and scaling to all possible actions and whether it's even feasible. So you can imagine maybe you can collect enough videos of kitchens and cooking, and you can spend enough on annotators that perhaps you can get a rich enough data set to really learn from it. But I'm wondering, like, do you think that is really the answer to sort of universal action understanding, or do you see like self-supervision and things like that enabling much better generalization to
I think the
never seen before?
And this is quoted from Rahul, one of our speakers, when we did a one-day consortium in London on video. Video is not one type. We have a lot of curated video online, whether curated means movies or curated means someone has cut a video to put it on social media. Continuing to only learn from these, despite their availability, is very limiting in our abilities. Natural videos are very hard to collect, but potentially is what we eventually need. Because it doesn't have that element of human intelligence in cutting and chop and shots, etc. So we would not know the eventual capabilities of our models until we have access to a good amount of natural videos. And my fear is when we do, which is coming very soon, we'll realize that our models are not really fit for purpose. So it's not only about learning from more data. So in my head, it's very much, let's collect natural videos and then realize our models don't really work. We fix them, and hopefully by then we have enough data to learn from them. I'm very much pro-learning. And I think the data is not only there to learn models, it's there to question how well our models work. And that's why small-scale test sets with very large self-supervision is very dangerous, because we'll think we've solved the problem. So we really need real test sets that are as large as what we train on.
So my second question was going to be in exactly this direction. So the semantic similarity thing you showed, I was sort of a bit depressed by that. Particularly Random was doing like very competitively on, I think, all of the benchmarks you showed. So, I mean, have we learned anything, or are we just overfitting to peculiarities of data sets?
We are learning something. But as I said, we're making lots of over optimism on how some models are doing better than others. That's the bit that needs attention. And I think we had a bit of work in 2017 where we just added one frame to a video and realized that all these models just don't work because they are trained on our annotations. And perhaps that's the reason why many people want to push for self-supervision, because our annotations are as biased as our data. So there is a lot of token data bias, less token annotations bias and labeling bias. And perhaps this is an effort to highlight the need to do fairer labeling. It's a chicken and egg problem. We were using these labels to assess our models, but yeah, they're not really good at the moment.
If I can ask a question. Okay, so that was all very exciting, but I think my particular interest here is it's actually similar to Will's last question about the linguistic ambiguities in your labels. This was one of the first challenges I tried to tackle with some of my colleagues when I arrived at York in the late 90s. We had a data set with two simple options, syntactic ambiguity. You had to go for one or the other. And it turned out that 15 to 20% of the sentences were genuinely ambiguous. I walked to to the hotel by the river or something like that. And then there is no way you can beat the system because you have to choose both, not either.
Correct.
And the obvious thing to do, it seems to me, which is probably exactly what you've done, is to go for some embeddings or synsets or whatever. And presumably, once you've gone for the embeddings of those phrases or sentences or whatever they are, presumably the results got better. And,
so
and you
in
can,
our in our data set, we have done the two steps. So we have free form sentences, but we also have a combination of automatic and manual relationships of verbs. So things like put and place and cut and chop. We have published what we call verb classes that relates them, saying these are actually when they can be replaced and when they can't be. And you can do that on a small scale data set. You probably can't do that on everything. And it's very much, we believe it's visually important to see also the example. So for example, if I say opening a door, there are many ways in which you can open a door. I can pull, push, slide. Now, if I look at the person opening the door by sliding, and then I look at an example of person opening a drawer by sliding, we can agree that these are related, but not every open door is related to every open drawer. So it's not even only in the language. Also, we've published paper that talks about verbs of manner and verbs of state, which makes language really hard. So if you ask a kid to open a door and they don't know how to open it, you might give them additional information like turn the handle and then pull the door. You're giving them the mapping between the objective, which is opening, and the manner. But when we write language, we don't have that mapping. That mapping is only in our head, and there is no ground truth for it. It's not written. It's not written. So written language is really very far from the language we need to train models. And everything that linguists have done in terms of giving verbs meanings is not of direct value to what we want in vision. So as you said, you're right. Our current approach is to try to figure relevance and do embedding. It still doesn't really give us what we call classes. So what's an open and what's not. So it's a solution to one problem, but it's not really a sufficient solution to knowing boundaries. And currently there isn't a problem or a model that is capable of doing both. So we either do retrieval, where something is more relevant than the other, or classification, And what we need is a sort of combination.
Great. If I can just a quick follow-on question. Actually two questions, but they're the same. Question one, do you think that embedding trained on just large text data sets, regardless of any videos, would help do what you do? And presumably you're already using, I don't know, something like, BERT or whatever. And question two, do you think any ontologies that you can find, ready-made ontologies of basic concepts and relations would be of any use to the things that you're doing, or maybe even extract those? I don't know.
We haven't found either. So BERT models are trained on Wikipedia sentences. They don't have anything like I opened the fridge and picked up my bottle. That's not written in any text. So there is no, BERT models are good in kind of getting you a structure of the sentence for us, but nothing more, not this level. We haven't found any ontology that is of use to us. And we've really looked, but we're not experts. At the moment, language on its own hasn't provided the level we are after, because they focus on written text and Wikipedia. Okay,
so that's three PhDs down the line.
Let's hope so. Let's hope not more, huh? Let's only that. I think there's a question from Rapi.
Yeah.
I saw in a video that opening a tab on top of bottle and opening a cupboard are classified as the same type, despite that they're very different actions people are doing. I wonder how the model handles this. So what the model is using as label is that it is being told that these two are open and they need to be close to one another than something closing, and that's only in that space. But then there is the ultimate space where they are made different. But in that space, they are encouraged to be close to one another. And the visualization is showing that this succeeds, right? That it doesn't really break the overall system. It improves the overall action accuracy a little bit, but more importantly, it's capable of actually saying all this is opening, which was the objective. So this is trained to be relatable or comparable through these triplets.